An important skill to have in a process control class is being able to identify and find the transfer function that is associated with a graph that you're given of the time domain function of some output. And so a common question one would expect to see would be, you'd be given an evolution profile of some output over time, and we would like to translate this into a transfer function. And so to do that, the first thing we'll do is we're going to analyze our graph here, and we're going to recognize that we have a gain of +2 in our transfer function, as well as a time delay of 2 seconds. So I'll call this seconds. So I'm going to let theta be equal to 2, and we'll get to what theta is later. And then in addition to that, we need to find what tau is, because we're trying to determine what y of s over u of s is. And as you'll recall, this has a standard notation, k divided by tau s plus 1. And if we have a time delay, we would also have an exponential term in here, minus theta s. And so in this case, we've identified k, we've identified theta, but this tau parameter is something we can also obtain by looking at when we are 63% of the way towards our new gain. And so when y is equal to 0.63 times the new gain, k, we can determine what tau is. And so in this case, we would multiply 2 by 0.63. So 2 times 0.63 is equal to 1.26. And so if we eyeball this plot here, 1.26 is approximately here. And if we look down here, we would find that at 5 seconds, we are 63% of the way towards our new equilibrium value. And therefore, our tau does not equal 5, but our tau is actually equal to 5 minus 2, because our function here is starting at 2 seconds. And so tau is equal to 3. And so now we have gotten a step closer towards defining our overall transfer function. Y of s over u of s is equal to k, which is 2 times the exponent of minus 2 times s, because we have a time delay, and our tau parameter here was equal to 3 times s plus 1. And so this is our transfer function that we've just arrived at. And so now what we're going to do is we're going to want to find the actual y of t value. And so y of t equals question mark if we subject our system to an impulse input. And what an impulse input means is that u of s is equal to 1. And we'll recall that the inverse Laplace transform of 1 is equivalent to a Dirac delta function of t. And so what we'll do is now we will say that y of s is equal to, carrying everything over from here, 2 times the exponent of minus 2s quantity divided by 3s plus 1. And we're going to multiply this by our u of s term, which was equal to 1 here. And another important mathematical relationship to recall at this point is that if we take the Laplace transform of some function that has been shifted to the left or right on a plot, take f of t minus t naught, for instance, this is equivalent to f of s times the exponent of minus t naught times s. And so what we should recognize here is that this exponent minus t naught s corresponds to this portion here, exponent minus 2s, and this 2 over 3s plus 1 is equal to our f of s. And so now if we just focus in on our f of s term, 2 over 3s plus 1, if we multiply the top and bottom by 1/3 to get this into the more standard notation, we would have 2/3 times 1 divided by s plus 1/3, and we will recall the definition of the inverse Laplace transform of this is equal to, we can pull out the 2/3 because it is a constant. If we also recall, if we take the Laplace transform of the exponent of at, for instance, what we get out is 1 over s minus a. A, in this case, will be equal to minus 1/3. So working backwards from that, sorry for having this a little screwed up, but what this is equal to is we would have 2/3 times the exponent of minus t over 3. And because we had this exponential term here, which was shifting our function over by t naught, we will now plug in everywhere we have a t minus, in this case, 2. And so what we ultimately arrive at is that our function y of t is equal to 2/3 times the exponential of minus quantity t minus 2, the shift, divided by 3. And the next thing to note here is if we plotted this function as a function of how our, to clarify, if we wanted to figure out how y deviates, the deviation of y is a function of time in seconds, what we would get if we were to qualitatively sketch it would be a plot that looks like this, in which we would have this exponential decay occurring. And so this concludes how we can go from a picture of visualizing an output into getting a transfer function. And then if we're given the input response, such as an impulse, we can ultimately find how the output will vary as a function of time, as well as get an idea of how its deviation from the nominal steady state value changes over time. And another thing to note here is that with impulse responses, we have an instantaneous and brief change, which is to say we see the effect of our step change immediately, and it is a finite change, which is what we observe in this graph, and we also realize exponential decay. And so I hope you guys find this useful in your process control class or on the job maybe. But let me know if you have any questions, and thanks for watching.